Imagine building a skyscraper, right? Where the foundation is, well, completely invisible. And the elevator shafts, they just scale to infinity.
Right, until you hit a hard mathematical limit.
Yeah,
And then that just throttles your entire enterprise.
exactly. And today we are taking a deep dive into SAP HANA Cloud. We're really bridging that massive gap between, high-level architectural theory and the exact command line syntax you actually need to build it.
Because when you deploy your enterprise data landscape in the cloud, those physical constraints like server racks and cooling systems, they're abstracted away behind these really sleek user interfaces.
Yeah, it feels like infinite computing. I mean, it looks like magic on the screen.
But the structural logic, the actual physics of memory bandwidth and the mathematics of data storage, those remain just as unforgiving.
Completely unforgiving. So, welcome to the deep dive. Our mission today is absolute mastery of SAP HANA Cloud provisioning, the underlying data tiering architecture, and the precise execution required to deploy it seamlessly. I'll be approaching this from the perspective of an enterprise architect, so I'll be focusing on the structural logic and dependencies.
And I'll be taking the perspective of the lead basis and functional engineer. So while the architecture gives us the blueprint, my focus is strictly on the exact execution.
Right. Getting our hands dirty.
Exactly. We are going to cover the specific transaction paths, the system limits, the configuration rules, and the exact command line interface syntax required to bring these architectures into reality.
Because when you're tasked with deploying your enterprise landscape, you can't just wave a wand and say, make it scalable.
You absolutely cannot. You need exact parameters. We are bypassing all the surface-level summaries today to deliver a highly technical, practical guide. So let's just jump straight into the first core architectural concept that dictates everything else: data tiering strategy and the storage mechanism.
Right. Let's unpack this overarching philosophy of SAP HANA Cloud data tiering. In any enterprise environment, the architecture is constantly fighting this war between performance and costs.
Always. It always comes down to budget versus speed.
Exactly. The high performance of in-memory computing, which is, let's be real, HANA's entire claim to fame, it's unparalleled.
Yeah.
But we have to balance that against the harsh reality of IT budgets and data aging.
Yeah, you just cannot keep 20 years of transactional history in RAM.
Yeah.
It would completely bankrupt the department.
Right. Where you store your data strongly depends on how often you access it, its type, its operational usefulness, and your security requirements. As data ages, it naturally becomes less relevant for real-time analytics.
So to solve this, SAP HANA Cloud relies on 3 distinct temperature tiers: hot, warm, and cold.
Okay, so hot data is your highly volatile, frequently accessed data. Warm data is accessed less frequently, and cold data is essentially historical. But looking at the architecture, a really crucial question arises. If cold storage is so incredibly cost-effective, why not simply route all historical data directly to the data lake upon creation? I mean, why do we actually need this intermediate, warm, native storage extension layer?
It's a great question, and it's actually one of the most common architectural debates. When you configure your storage strategy, you have to understand the technical execution of these tiers to answer that. Let's break down the exact mechanisms.
Let's do it.
So, hot data is stored entirely in memory, directly in the RAM. This provides the highest performance for real-time processing, but inherently, it carries the highest total cost of ownership, or TCO.
Right, because RAM is incredibly expensive.
Exactly. So if you routed everything else directly to cold storage, you would introduce massive latency for data that is still operationally relevant, but just not accessed every single millisecond.
Right, like think of a financial closing period. You might need to rapidly query data from 3 months ago.
It's not hot today, but when the CFO needs the quarterly report, it better act like it is.
Oh man, yeah. Sending that 3-month-old data to a cold data lake means you're suddenly dealing with disk spin-up times, network latency, federation overhead. The CFO's dashboard goes from loading in 2 seconds to loading in 2 minutes.
And nobody wants that meeting.
Right.
Precisely. And this is where the warm tier, driven by the native storage extension, or NSE, becomes totally critical.
Okay, so how does NSE actually work?
The native storage extension integrates disk or flash-based storage directly with the in-memory database. From an engineering perspective, the technical formula for your database capacity fundamentally changes.
How so?
Well, if you only use the hot tier, your standard capacity equals the exact amount of hot data you can fit in memory. But when you leverage NSE, your database capacity equals the hot data in memory plus the warm data on disk.
Wait, that formula completely alters how we architect the memory landscape. Because we are no longer strictly bound by the physical RAM limits for active datasets, we're in a way artificially extending the effective memory footprint.
Exactly. You are extending it.
But how exactly does the underlying mechanism handle this without degrading the in-memory performance that SAP HANA is known for? I mean, disk is disk. You can't just pretend it's RAM.
You can't pretend it's RAM, no. But you can be incredibly smart about how you move data between the two. Think of your RAM as your kitchen counter. That's your hot data space.
Okay, makes sense.
And the disk storage is your deep freeze, holding the warm data. The NSE underlying mechanism relies on an intelligent buffer cache. This cache specifically manages memory pages for the NSE column store tables.
So it's not pulling everything at once.
No, it acts like a highly efficient prep station. When you query warm data, the system does not load the entire massive table from the disk into the RAM. Instead, it pages the specific data blocks needed into this intelligent buffer cache.
Ah, I see.
Yeah, it only thaws the specific cuts of meat you need for the dish you're cooking right now.
That is a brilliant analogy. So it's working at the block level, not the table level. That is a massive distinction.
It's a game changer.
Because if I have a billion-row table marked as warm, and my query only hits 50,000 rows for a specific date range, the buffer cache only pulls the memory pages containing those 50,000 rows into RAM.
Exactly. And what is really critical here is that this mechanism supports all the advanced SAP HANA features you already rely on. It maintains column-level compression, it utilizes dictionary support, and it honors table partitioning.
So it's completely seamless to the end user.
Completely. It coexists perfectly with the standard SAP HANA in-memory column store. You can even join a hot table strictly in RAM with a warm table managed by NSE, and the SQL optimizer handles the execution plan perfectly.
That's incredible.
And for execution, you must note a very important operational detail. The SAP HANA native storage extension is enabled by default in an SAP HANA Cloud database instance.
Oh, so I don't have to install a plugin or anything.
Nope, you do not have to run a specific command to install the NSE engine. You simply utilize it by specifying the page loadable parameter when you create or alter a table.
Okay, so we have the hot tier in RAM for instant access and the warm tier on disk managed by the intelligent NSE buffer cache for high-capacity operational data. That naturally brings us to the cold tier, which relies on the SAP HANA Cloud Data Lake.
Right, the data lake.
Architecturally, this is built on the SAP Relational Engine backbone, which, veterans will remember as SAP IQ.
Oh yeah, good old IQ.
Yeah. This is a columnar engine designed for massive petabyte scale storage of structured and unstructured data. It is kept independent from the primary HANA compute node, yet heavily integrated for federated querying.
Yes, and that independence is key,
Yeah.
because you really don't want petabytes of historical data bogging down your primary transactional engine.
Right. Keep them isolated.
But when you configure a standalone or integrated data lake, you must explicitly understand your ingestion limits and specifications. You can't just dump a petabyte of data into it on day one and expect it to swallow it instantly.
Right. Let's talk about those guardrails. What are the exact physical limits we are dealing with when provisioning the data lake?
For the initial configuration, the storage starts at exactly 1 terabyte. It scales up to a maximum of 90 terabytes per instance, and it scales strictly in 1 terabyte increments. You can't just add 500 gigs, you provision in full terabyte.
Got it. And the compute.
On the compute side, the maximum compute capability you can allocate to a data lake is 162 vCPUs. But the most critical execution detail you must calculate, and this is where I see a lot of data migrations just fail, is the ingestion math.
The ingestion math. Let's break that down, because this is where architectural theory really hits a brick wall in reality.
Exactly. When you are moving massive historical data sets into the data lake from external object stores like, say, Azure Blob or Amazon S3, the ingestion rate is hard-capped.
Hard-capped at what?
The formula is exactly 1 terabyte per day per dedicated vCPU per table.
Wait, per table?
Yes, per table.
So if I have a massive historical sales table that is, say, 5 terabytes, and I have allocated 2 vCPUs to my data lake, how fast can I ingest that specific table?
You can ingest 2 terabytes per day for that table. So it'll take you 2.5 days to migrate that single table.
Wow. Okay.
Yeah, if you write a script that tries to parallelize the load and blast all 5 terabytes into that table in a single hour, the system will throttle you. Your pipeline will choke.
That is brutal.
And furthermore, there is an absolute maximum ingestion limit of 16 terabytes per day per table, regardless of how many vCPUs you throw at it. You must design your batch jobs, your initial migration loads, and your ongoing data aging runs around these exact mathematical limits.
That is a really critical operational constraint. I mean, if I'm an architect planning a weekend cutover for a 20 terabyte monolithic table, I physically cannot do it in a 48-hour window. The math just forbids it.
It absolutely forbids it.
So I would have to, what, partition the source data into multiple tables to parallelize the ingestion across different table targets?
Right.
Or just completely rethink the migration timeline?
Exactly. You engineer around the limit by splitting the load. And from a security perspective, while the ingestion requires careful planning, the user access is surprisingly elegant.
I was actually just going to bring that up, because from a security architecture standpoint, mapping permissions across hot RAM, warm disk, and a completely separate cold data lake engine, theoretically, that could be a nightmare.
Oh, a total nightmare.
You'd have to synchronize roles across multiple databases, but the architecture dictates that the data lake automatically inherits the security and data protection models of the primary SAP HANA Cloud instances.
Yeah, it is natively federated. There's no manual configuration required to duplicate roles or privileges to the cold tier.
That saves so much time.
It really does. If a user has select privileges on a view in HANA Cloud that federates data from the data lake, HANA handles the remote execution securely. You access and query this cold data transparently via the Database Explorer as if it were a local table.
Okay, so the engine just translates the SQL, pushes the execution down to the SAP IQ backbone, and returns the result set securely. Exactly.
Transparently and securely.
Okay, so we've established that relying entirely on in-memory RAM will bankrupt our IT budget, hence the tiered storage strategy. We understand the limits of hot, warm, and cold, but getting that tiered architecture off a whiteboard and into a real environment means navigating a surprisingly strict set of validation rules. How do we actually deploy this?
The transition from theory to reality happens in the graphical user interface.
Okay.
Well, at least initially. The architectural entry point for deploying these concepts is SAP HANA Cloud Central, which is located within a fresh SAP Business Technology Platform, or BTP, account.
Right, let's set the context for BTP for a second. The SAP BTP account acts as the overarching global container. It is the hyperscaler abstraction layer. When we provision an instance, we are mapping our architectural blueprints into concrete cloud resources, compute, memory, and storage, within a specific region and sub-account in this central environment.
Exactly. And for the precise execution path, you will log into your SAP BTP subaccount, navigate to SAP HANA Cloud Central, and just walk through the provisioning wizard. When you click the Create Instance button, you are immediately faced with a critical decision regarding the instance type. You are presented with 4 options.
And this decision dictates your entire deployment methodology. Let's walk through them.
First, select a preset. This provides standard SAP configurations for development or productions. It's basically the quick start method.
Okay.
Second, use JSON configuration. This is incredibly powerful. It allows you to pass a JSON file containing all your exact parameters. You use this for rapid, identical deployments across multiple environments, which, is essential if you are building automated CI/CD pipelines.
Right, infrastructure as code.
Exactly. Third, configure manually, where you select every toggle yourself. And fourth, create a cloned SAP HANA database, which just takes an existing instance and duplicates it.
So when you are provisioning an enterprise landscape and you require full architectural control to understand every single variable, which path are you taking?
You must select the Configure Manually radio button. This forces you to acknowledge every constraint. Let's look at the basics and admin setup. Unlike legacy on-premise SAP deployments, where the system ID, or SID, was strictly limited to 3 alphanumeric characters, like PRD or DEV, the cloud architecture provides much more descriptive freedom, but it enforces its own rules.
I remember the days of fighting over 3-character SIDs. It was a nightmare for naming conventions, like, is PR1 Production 1 or Payroll 1?
Oh, I've had those exact fights.
Right. In the cloud, the instance name must be between 1 and 63 characters long. The description constraint is between 1 and 255 characters. This isn't just a cosmetic UI update. I mean, it completely changes how we can implement naming conventions for massive multi-tenant environments. You can embed the region, the business unit, and the environment tier directly into the 63-character string.
It's so much better. It allows for strict metadata tagging right in the name. But once you name the instance, you hit a crucial execution detail regarding the administrator account. In SAP HANA Cloud, there is no system user.
Hold on. Say that again. Every basis administrator on Earth knows the system user. It is the root account of SAP HANA.
Not in the cloud. The system user from on-premise HANA does not exist here. The initial super-user is named DBADMIN. When you configure the DBADMIN password in the wizard, it must meet exact string requirements. A minimum of 8 characters, at least 1 uppercase letter, at least 2 lowercase letters, and at least 1 number.
Okay, so DBADMIN is the new root key to the kingdom, and this is where architectural security policies directly impact daily operations. Because if you treat DBADMIN like the old system user, you are walking into a massive trap, aren't you?
A catastrophic trap. And this is honestly the biggest troubleshooting and operational gotcha for new cloud deployments.
Let's hear it.
When you provision this instance, you must immediately, on day 1, create secondary administrative roles and dedicated technical users. Why? Because the DBADMIN password is subject to a hard-coded default security policy that expires the password after exactly 180 days.
Wait, 180 days? So if I use DBADMIN to set up my automated ETL batch jobs or, if I hard-code it into an application connection string, what happens in 6 months?
In exactly 180 days, your production integrations will completely fail.
Just dead.
Dead. The password expires silently in the background, your batch jobs will throw authentication errors, your BI dashboards will go offline, and you will be scrambling to figure out why the entire landscape just crashed.
Oh, wow.
Yeah, you must not use the DBADMIN user for daily batch jobs, application connections, or automated reporting. DBADMIN is for initial provisioning and emergency break glass scenarios only.
Good to know.
You log in, you create a dedicated technical user with a password policy that does not expire, or, well, better yet, relies on certificate-based authentication, and then you lock away the DBADMIN credentials.
That is a phenomenal piece of engineering advice. The architecture enforces security, but it's up to the execution layer to actually build the operational runbook around it. Before we leave the GUI wizard, we have to talk about versioning. Because in the cloud, you don't just download support packages and apply them manually over a weekend.
Exactly. In the final GUI step for basic setup, you must select the version. SAP operates on a quarterly release cycle known as the QRC. The wizard allows you to select the current QRC, or you can select from the previous 2 QRCs.
So N, N-1, and N-2. Why would an architect choose an older version for a brand new deployment? Why not always just take the latest features?
Stability and regression testing. If you have a massive production landscape validated on QRC1 and you need to spin up a new QA environment in QRC3, you might want to force the new QA environment to match production exactly.
That makes sense.
Yeah, you select the older QRC to ensure absolute binary compatibility until you are ready to upgrade the entire landscape simultaneously.
That makes perfect sense. So that covers the basic instantiation. We have a name, a super user, and a version. But an instance is completely useless without defined compute power. I mean, the engine needs horsepower.
It does.
This brings us to the core of performance architecture: compute memory ratios and system limits. From an architectural perspective, workloads dictate infrastructure. But in SAP HANA Cloud, you cannot simply demand an arbitrary mix of hardware. Like, I can't just request 64 vCPUs and 32 gigabytes of RAM because I want high compute with 0 memory overhead.
No, you cannot. The architecture enforces a strict dependency between virtual CPUs and memory. You cannot arbitrarily select vCPU counts. They are inexorably bound to strict compute memory ratios.
Let's explain why SAP locks these sliders. It really comes down to the physics of the underlying hardware, specifically NUMA nodes non-uniform memory access.
Right, the UMA architecture.
The CPU needs immense memory bandwidth to scan billions of rows in RAM per second. If you artificially starve the virtual CPUs of memory, or if you assign so much memory to a CPU that it has to constantly traverse across different physical sockets on the host motherboard to find its data, the in-memory engine physically cannot move data fast enough.
It just bottlenecks.
Exactly. The sliders and the cloud UI exist to keep you from building a hardware bottleneck. They ensure that the vCPU to RAM ratio perfectly aligns with the physical NUMA topology of the hyperscaler's hardware.
Exactly. The UI basically protects you from building a poorly optimized engine. As the engineer configuring the system, you must select the correct performance class, which then dictates the exact slider ranges available to you. Let us break down the exact ratios and the concrete scenarios where you use them.
Let's start with the edge cases and work our way to the standard.
Okay, first, the high compute class. This operates on a strict 1.4 ratio. This class gives you between 8 and 90 vCPUs, paired with 32 to 360 gigabytes of RAM. You select this when your workload is highly compute-intensive, but requires a much smaller memory footprint.
Give me a concrete example of when I would deploy a 1.4 high compute system.
Imagine a scenario where you are heavily utilizing the SAP Agent Predictive Analysis Library or running complex Monte Carlo financial simulations.
Okay, heavy math.
Right. The data set itself might only be 50 gigabytes, but the mathematical transformations you are running on that data require massive parallel CPU threads. You don't need a terabyte of RAM, you need raw processing power.
Right, understood. What's the next tier?
Second is the compute class, which operates on a 1.8 ratio. This scales from 4 to 144 vCPUs with 32 to 912 gigabytes of RAM. This is a balanced step up, often used for data marts with moderate data volumes but heavy reporting demands.
So a bit more breathing room for the RAM.
Yes. And third is the default class. This provides a ratio between 1.13 and 1.1 steam. This is the massive workhorse. It scales from 2 all the way up to 440 vCPUs, paired with 32 to 5,970 gigabytes of RAM.
Wow, nearly 6 terabytes of RAM. So when you are deploying standard enterprise workloads like your core SAP S4 HANA backend or a massive enterprise data warehouse, this 1.1 seat ratio is really your baseline configuration.
Correct.
It provides the optimal balance of memory to hold the hot data and enough CPU threads to serve thousands of concurrent user queries.
Absolutely. But then we have the absolute extreme, the high memory class. This operates on a massive 1.30 ratio. It is completely fixed at exactly 120 vCPUs and 3,600 gigabytes of RAM.
Wait, let me stop you right there. 120 vCPUs paired with 3.6 terabytes of RAM. That is a massive 1.30 ratio. In what world am I deploying that instead of scaling up the default class? Like, what is the specific use case for starving the CPUs relative to the memory footprint?
You deploy the high memory class specifically for processing massive wide data sets that require heavy memory buffering and massive in-memory joins, but relatively simple calculations.
Ah, okay. Like what?
Think of a scenario where you have billions of rows of IoT sensor data or, raw unaggregated telecommunications logs. You aren't doing complex predictive math on them. You're just storing them in RAM and performing massive aggregations like SEM or count across billions of records.
Right.
You need the memory space to hold the data and perform the joins, but you don't need 400 CPUs to calculate a simple sum.
That perfectly illustrates how workloads dictate infrastructure. But these ratios define the physical envelope of your paid production capabilities. What happens when an architect just wants to prototype? There is a very specific limitation when you are testing architectures in non-production free environments.
Yes, and this trips up a lot of developers.
Yeah.
When you provision a developer sandbox in the SAP BTP free trial account, you must remember that you cannot alter these configuration sliders at all.
Not even a little bit.
Not at all. You are strictly capped. In the trial account, your instance is locked at exactly 16 gigabytes of memory and 80 gigabytes of disk storage. You cannot scale beyond that. If you try to deploy a massive data set to test your native storage extension tiering in a free trial, you will hit the 80 GB disk wall immediately.
Because it's a sandbox, right? Not a free playground for enterprise data.
Yeah.
So, assuming we are back in a production environment with our compute memory ratios properly allocated and funded, we have a highly tuned, screaming fast database.
No, we do.
But a single database is a single point of failure. We must now design for catastrophe. Let's talk about high availability, resilience, and network architecture. Let us deconstruct the architectural diagram for system resilience.
At a base level, the architecture looks like this. A client PC connects securely, which we usually represent in diagrams with those encrypted network padlocks, to the RAM of the primary SAP HANA Cloud instance. That instance is operating in a specific physical data center, let's call it Availability Zone A. Simultaneously, automated backups act as a completely separate fail-safe layer. These backups connect directly to the RAM state, piping data out to secure independent object storage on a scheduled frequency.
So we have the primary engine running in Zone A and backups saving the state. But, backups take time to restore. If Zone A catches fire, the business is down until we rebuild the system from those backups.
Yes, and that downtime costs money.
Exactly. And here is the architectural pushback I hear from risk management all the time. If an enterprise wants maximum data safety and absolute zero downtime, why don't we just deploy multiple synchronous replicas across every single availability zone globally? Like, let's put a synchronous replica in Zone A, Zone B, Zone C, and one in another country just to be safe.
You can't do that because of the strict financial and physical limitations of the execution layer. Replicas are not just logical ghost copies or lightweight snapshot pointers. They are fully provisioned, running database instances.
Oh, so they cost real money.
Real money. When you deploy a replica, it incurs an exact one-to-one capacity unit cost based on the CPU, memory, and disk size of your primary instance.
So if I have a 6 terabyte default class system that costs, say, $20,000 a month in compute, adding a replica instantly doubles the bill to $40,000. Adding 4 replicas makes it a $100,000 monthly burn rate just for redundancy.
Exactly. Because of this massive cost multiplication, SAP structurally restricts the architecture. You're limited to a maximum of exactly 2 replicas. You cannot build a global mesh of 20 replicas. Therefore, to balance cost, performance, and risk, the configuration rule you must follow is very specific.
What is the exact deployment rule for these 2 allowed replicas?
When you configure high availability, you must set one replica as synchronous. And this synchronous replica must reside within the same availability zone as your primary instance.
Let's unpack the physics of that. Why must the synchronous replica be in the same availability zone?
Because of the speed of light and network latency?
Oh, physics again.
Always physics. In synchronous replication, when a user commits a transaction, the primary database will not return a success message to the user until the replica has also written that transaction to its log.
Right, so they are locked together.
Exactly. If you put the synchronous replica in a data center 500 miles away, every single transaction incurs network travel time. Your blazing fast in-memory database suddenly feels incredibly slow because it's waiting on a cross-country ping.
That makes total sense.
By keeping the synchronous replica in the same availability zone, the network latency is sub-millisecond. This provides instant failover with zero data loss for local hardware failures, like a specific server rack losing power.
Okay, so the synchronous replica protects us against a local hardware failure in Zone A without killing performance. But what if the entire Zone A data center goes offline? Like a flood, a massive power grid failure?
That is exactly what the second replica is for. You must set the second replica as asynchronous. This asynchronous replica must reside in a different availability zone, such as Zone B or Zone C.
And because it's asynchronous, the primary database doesn't wait for it. The primary commits the transaction, returns success to the user, and then streams the logs over to Zone B in the background.
Exactly. This protects against regional disaster recovery scenarios, where an entire data center goes offline. You might lose a few milliseconds of in-flight data in a hard crash, but the business survives a catastrophic regional event without suffering the massive network latency penalties during normal operations.
So the synchronous replica ensures continuous operation within the local data center, while the asynchronous replica protects against regional failure. It is a perfect architectural balance of physics, risk, and cost.
Precisely. And to model the exact financial impact of this architecture before you ever deploy a single line of code, you must use the SAP HANA Cloud Capacity Unit Estimator tool.
I love that tool.
It's essential. This public tool allows you to plug in your vCPUs, memory, disk, and your replica strategy, and it will calculate the exact monthly capacity unit cost. You never guess the cloud bill, you calculate it mathematically beforehand.
Okay, so now we have a foundation that is highly performant with NSE tiering, properly sized with NUMI-aware compute ratios, and deeply resilient with sync and async replication. The core database is rock solid. Now we can start enabling the specialized engines.
Let's do it.
Architecturally, SAP HANA Cloud exists within the SAP BTP multi-environment, which heavily utilizes Cloud Foundry space mapping. We isolate specific workloads through highly specialized native services running within the cluster. We do this rather than forcing all complex operations like vector math, natural language processing, or graph traversal through standard SQL processing, which is honestly terribly inefficient for those tasks.
Right. A relational database is great for rows and columns, but it's terrible at understanding the semantic relationship between a node and an edge in a knowledge graph.
Totally.
So during step 5 of the provisioning wizard, which is the advanced settings phase, you will execute this architectural isolation by toggling specific native engines on or off. Let us walk through the exact toggles and their concrete use cases.
Let's start with the script server. What does that actually do?
You must enable the script server. If your application requires the execution of application function libraries, or AFLs, written in C++11. These are complex, pre-compiled algorithms, often used for deep predictive analytics or specialized business logic, that need to run directly alongside the data in memory, rather than pulling the data out to an external application server.
Oh, I see. It pushes the code to the data rather than pulling the data to the code. Classic HANA paradigm.
Exactly.
Next toggle, the document store.
You enable the document store if your workload requires native JSON document operations.
Explain how that works in practice. Why do I need a JSON document store inside my relational SAP database? Why not just use a dedicated NoSQL database like MongoDB?
Because enterprise data is messy. Imagine you have a standard, highly structured relational table containing customer IDs and billing addresses, but your web application captures user profile preferences as massive, deeply nested, unstructured JSON files.
A very common scenario.
Right. If you use a separate NoSQL database, you have to build complex data pipelines to combine them. By enabling the document store inside HANA, you can natively join those unstructured NoSQL JSON documents directly with your standard relational column store tables in a single SQL query. The engine handles the bridging.
That is incredibly powerful for modern web app development on BTP. You get the strict ACID compliance of a relational database joined instantly to the flexibility of NoSQL.
It's fantastic.
What about the triple store toggle?
You toggle the triple store on for the binary storage and processing of knowledge graphs. Specifically, it stores data as triples in the Resource Description Framework, or RDF, format. A triple is basically subject-predicate-object, like user A, purchase product B.
So if a company is trying to build a complex semantic web or a deep recommendation engine that maps how every product, customer, and supplier relates to one another in a massive web of connections, they turn on the triple store. It traverses those relationships infinitely faster than writing a SQL query with 50 join-on statements.
Exactly. Next is the NLP toggle, or natural language processing. You must enable this if your workload requires text analysis.
And in the era of generative AI, this is becoming the most critical engine.
Absolutely. NLP allows the database to tokenize massive blocks of unstructured text and generate dense vector embeddings. If you are building retrieval augmented generation, or RAG architectures, where a large language model needs to search your corporate documents for context, this engine provides the native vector search capabilities.
It essentially turns ASYN into a vector database.
Yep. And finally, we have the Data Provisioning Server, or DPS.
Right.
The Data Provisioning Server is a highly critical component for integration. It is a native index server variant that runs directly inside the HANA cluster.
Why does it matter that it runs inside the cluster?
Because historically, data federation required external middleware servers. By enabling the DPS, you turn on SAP HANA Smart Data Integration, or SDI, directly on the database node. This engine provides real-time and batch mode data transformations, data quality functions, and houses the adapter SDKs necessary for connecting to remote external sources like Oracle databases, Hadoop clusters, or external APIs.
So instead of buying and maintaining a separate ETL server, the HANA database itself reaches out, grabs the remote data, cleans it, and ingests it.
Exactly.
But these native engines, whether it's the SDI reaching out or the NLP engine processing web text, they dramatically expand the compute capability. However, they also expand the attack surface. If the network isn't strictly controlled, you have a massive intelligence engine sitting exposed.
Which brings us to the network allow listing execution. You cannot just leave the front door open. In the setup, you have three distinct architectural options for inbound traffic. Option 1, allow only BTP IP addresses.
This is the most secure posture, correct?
Yes. It means your database is strictly internal. It rejects all traffic from the public internet. It can only be accessed by applications or services that reside within your specific SAP BTP environment.
And option 2?
Option 2, allow all IP addresses. This exposes the connection endpoints to the public web. You would generally only use this in a highly transient development sandbox, never in production.
Definitely never in production. And option 3?
Option 3, allow specific IP addresses and IP ranges. You configure this option using CIDR blocks to allow traffic only from your corporate VPN routing gateways or specific branch office static IPs.
Okay, so that secures the inbound traffic to the cloud. But what about the outbound traffic? What if my HANA Cloud instance, using that smart data integration engine we just talked about, needs to query a legacy SAP ERP system sitting on a physical server in my company's basement? I can't just open a firewall port in my corporate basement to the public internet. That violates every security policy in existence.
No, you absolutely do not open inbound firewall ports to your on-premise network. To solve this, you must execute the Cloud Connector configuration.
Let's deep dive into the Cloud Connector because the mechanism here is brilliant.
It really is. The Cloud Connector is a small piece of software you install on a server inside your corporate network. It acts as a reverse invoke proxy.
Reverse invoke. Explain exactly how that circumvents the firewall problem.
Well, a standard proxy waits for inbound requests. A reverse invoke proxy works from the inside out. The Cloud Connector sits securely behind your corporate firewall and reaches outbound to the SAP BTP environment to establish a persistent, secure TLS tunnel. Because the connection is initiated from the inside going out, your corporate firewall allows it without requiring you to open any dangerous inbound ports.
So the tunnel is built from the basement up to the cloud. And once that tunnel is
Once
established,
the tunnel is open, the SAP HANA Cloud instance can send queries back down that exact same secure tunnel to query your on-premise assets.
that is so elegant.
It allows the cloud to seamlessly query the basement without exposing your internal corporate landscape to the outside world. Furthermore, the Cloud Connector features automatic recovery of broken connections. It supports high availability clustering so it doesn't become a single point of failure, and it maintains strict audit logging of all traffic passing through the tunnel.
It is the secure bridge between the legacy world and the cloud world. And wrapping up the security architecture, we must address encryption keys. The cloud provider encrypts the disks by default, but for high-security environments like defense contractors or healthcare providers, trusting the cloud provider's keys just isn't enough. The architecture relies on the integration of the Key Management Service, or KMS.
Yes, as a critical security action item, you must integrate the BTP KMS with SAP Data Custodian. This enables the Customer-Controlled Encryption Key, or CCE, feature.
Customer-controlled, meaning SAP doesn't hold the keys, the hyperscaler doesn't hold the keys, the customer holds the keys.
Exactly. You generate the master root keys in your own external vault. HA Cloud uses those keys to encrypt the data at rest. If you detect a breach, or if you terminate your cloud contract, you simply revoke access to your key in your own vault.
And what happens then?
Instantly, the entire petabyte-scale database in the cloud becomes cryptographically shredded, unreadable ciphertext. This guarantees that the enterprise maintains absolute cryptographic control over their data, regardless of where it physically sits.
It's the ultimate kill switch.
Yeah.
Okay, up to this point, we have mapped everything through the GUI. We've clicked buttons for tiering, sliders for compute ratios, radio buttons for replicas, and toggles for security. But enterprise architecture at scale demands repeatability, version control, and automation. If I need to deploy 50 identical QA databases across 3 continents, I'm not paying an engineer to click through a wizard 50 times and hope they don't make a typo.
Oh, please don't.
Right. This dictates a shift from manual GUI provisioning to automated scalable deployment via the command line interface. Infrastructure as code is not optional at scale. It is mandatory for integrating into CI/CD pipelines. This brings us to our final technical segment, CLI automation.
Yes. When you execute infrastructure as code, you bypass the wizard entirely. You deploy the entire architecture via JSON payloads executed in your terminal. If you're scripting this in the CLI, here's the syntax you'll actually use. Step 1. You must authenticate the Cloud Foundry CLI against your BTP environment.
What is the exact command string to open the door?
The exact command is cflogin SEO organization nes space SEI API endpoint.
Let's break down those flags for the listener.
Sure. The F flag defines the exact BTP organization you are targeting. The S flag defines the specific Cloud Foundry space, like your specific dev or prod container that you are deploying into. The GAU flag defines the regional API endpoint, which tells the CLI which physical hyperscaler data center to talk to, like US East or Europe Frankfurt.
Got it. Step 2. Once authenticated, we execute the creation command. This is where the magic happens.
You must understand the exact syntax structure for provisioning. The command is cf create service, offering service plan service, name-date, memory.x, system password.
The absolute power here is the JSON payload injected via that NAICS flag. That payload replaces every single click we just talked about. That payload mathematically defines the architecture, the compute ratios, the allow lists, the replica configuration without any human intervention or UI latency.
Let us run a concrete scenario to tie it all together. Suppose you're tasked with deploying a 64-gigabyte database named HC200 database via a scripted deployment pipeline. You need to set the initial DBADMIN to welcome 1. You must execute the following exact string in your terminal.
Ready.
CF create service, HANA Cloud, HANA HD200 database, NIXI, memory, 64, system password, welcome 1.
And the system parses that string, spins up the containers, allocates the 64 gigs of RAM, configures the storage, and hands you back a fully functioning enterprise database.
It does. But as a final troubleshooting reminder on CLI execution, if you execute this exact string while logged into a free trial account space, the deployment will instantly fail.
Because of the free tier limits we talked about.
Exactly. Remember the physical limits we discussed earlier. In the trial account, the memory parameter inside the JSON payload cannot exceed 16. If you pass 64, the API validates it against your license tier and rejects the payload with an error. You must always ensure your infrastructure as code scripts are dynamically aware of the environment limits they are deploying into.
That is a brilliant tieback to the structural constraints. Let's summarize the massive technical journey we have mapped today. We began by defining the core storage reality, balancing hot in-memory data against the intelligent buffer cache of warm disk storage, and navigating the strict 1 terabyte ingestion limits of the cold data lake. We translated that theory into execution, defining why new MA architecture enforces the strict vCPU to memory ratios that govern the compute classes.
And we architected system resilience, establishing the precise rules dictated by the speed of light for deploying a synchronous replica in the same availability zone and an asynchronous replica in a different zone to protect against regional disasters.
We isolated specific workloads using the native document store for JSON NoQuel integration, the triple store for semantic graphs, and the NLP engine for vector generation. We secured the entire perimeter using reverse invoke proxies via the cloud connector, locked it down with customer-controlled encryption keys, and finally, we abstracted that entire incredibly complex process into an automated, scalable Cloud Foundry CLI JSON payload.
If you followed along, you now possess the precise transaction paths, the system limits, and the exact command line syntax to deploy this infrastructure flawlessly in a real-world enterprise environment. You have the blueprint.
You do. But I want to leave you with a final architectural challenge to explore on your own. You now have a flawlessly provisioned, highly resilient SAP HANA Cloud instance. You know exactly how the buffer cache intelligently pages warm data blocks into memory. But look ahead to the SAP roadmap. How might the integration of generative AI, specifically the Joule Assistant, which is being deeply embedded directly within SAP HANA Cloud Central, fundamentally alter the way you as an administrator operate?
That's a huge question.
Think about it. Right now, you monitor buffer cache statistics manually to tune performance. But how will a natural language model interacting directly with the system schema and telemetry data change the way you write SQL queries against this complex multi-tiered architecture in the future? When the architectural blueprints are no longer just executed by a static CLI script, but dynamically optimized in real time by an AI agent that understands the exact NUMA and topology better than we do, the way we build and manage the skyscraper changes entirely.
It changes from manual engineering to autonomous orchestration. That is definitely the next frontier.
Something to think about the next time you write a JSON payload. Thank you for joining us on this deep dive. Spin up your sandboxes, test these limits, and we will see you next time.